we'll skip over that night. And then I'm going to throw another curve at you. Not just that I missed last week, but I'm taking a vacation the second week in November. I'm going to be in Paris. Ooh la la, my wife. Ooh la la la. And I won't be teaching that particular week. So we're going to skip over. In other words, the class started last week on October 1. The 8th week won't be till December 10th. There's like 3 gaps in there. So which date is which is on this sheet. And what I expect to cover in each particular night is on that sheet. So I'll tell you in advance, and I'll even remind you with email since you were kind enough to give me your contact information, and let you know before that particular date with a little gentle reminder, hey, we're not meeting this week, we're meeting the next week. You won't show up here unnecessarily. Okay, where to go? Reactants. Oh yeah, that's good stuff. I think Greg, if I remember from the tapes, threw out a couple of equations. And he said, sort of wish he hadn't, but he did anyway. This inductive reactance is J omega L, and this capacitive reactance is 1 over J omega C. That's all correct. I wouldn't start with that. I would get there eventually. There are easier ways to make sense out of that stuff, but we'll get there. That J, which is, of course, as he explained to you, the square root of -1, the imaginary number. You'll say, I took algebra in high school and they didn't use J, they used I. The imaginary number is the square root of -1. Yes, they did. But we're using I for current. We don't want to confuse you, so we picked J. That's the only reason. It's done as a bookkeeping technique. If you have a circuit that has a resistor and a capacitor in it, it's going to have an impedance Z that has 1 part resistance and 1 part reactance. And there'll be a number in front of this. There'll be, you know, so many ohms of R and so many ohms of X. And that's, as I said, a bookkeeping thing, so you can keep the resistive and the reactive parts separately because they have to be treated differently when you're resolving equations, like the equations that you saw on how do you add series impedances, how do you add parallel impedances. That becomes really problematic because if you've got a capacitor in parallel with a resistor, remember the thing he said, R1, R2 over R1 plus R2 is a shortcut if you only have 2 devices in parallel? Those are the 2 things you got to multiply and add together. Try doing that sometime. It means combining a lot of terms. There's a shortcut for that too. You'll get there. Stick with me, it's in the course. Come back to it in a minute. Let's just, for the fun of it, start with a capacitor. It's a little easier to understand than anything else. Here's my voltage source. A voltage source, by the way, is anything that produces a constant voltage. And it's usually, symbolically, something with an open arrow next to it, you know, so that you get a plus and minus here. But not necessarily. It can also be something like this, which produces alternating current. This is an AC voltage source. This is a DC one. DC because it's always plus up here and it's always minus here. There's no plus and minus here because it's plus sometimes and minus other times. It's constantly alternating between plus and minus. It's reversing itself. So you have to take note of that. That's a voltage source. Is there such a thing as a current source? Ooh, betcha. There's a perfect example of a current source. You'll say, wait a minute, that's a short circuit here. I see a conductor here with no load, no resistance. Yeah, but it's a current source. It will produce a constant current no matter what. This will produce a constant voltage no matter what the load is. How can you have something like that? Well, I'll give you an example of something. It's called a transistor. Here's a transistor circuit. This stuff I'm putting on here, these resistors are to bias it, which controls the current that flows here, which controls the current that flows here. And that current here is governed by this current here. The current that flows to the base, the emitter of the transistor, controls the current from the collector to the emitter of the transistor. And it will do it in just that sort of way. It doesn't matter if it's a short or an open circuit there. It will give you a constant current. I shouldn't say that. In theory, you can't have an open circuit, one where there's a break in it, if you have a current source, because the current source means you got to produce current no matter what. The voltage would have to be infinite if there were a gap here. Similarly, if you had a short circuit here, you'd have an infinite current flowing through it. So you need some kind of resistance here. You really should have some there too. Just aside, let's go back to our point here I'm trying to make, which is, let's talk about that little guy called the capacitor. And obviously we're going to talk about transistors too. That's going to be in the course, and you're going to learn how they work, what's so wonderful about them, and how easy it is to understand what they do. I'm going to have another schematic symbol here for your entertainment called a switch. There are the switches open because there's a gap. When it's closed, the current flows through it because there's no gap. You know how a switch is. Open, closed, open, closed. Here is a capacitor. Now, that schematic symbol pretty much describes what it looks like. You've got a conducting plate here, and you've got a conducting plate here. These two plates are close together, but they don't touch. You have you basically have two conducting surfaces with a non-conducting something in between, called a dielectric. Dielectric meaning it is not going to conduct electricity. But this surface does, and this surface does. So if I turn on that switch, charges, current is actually going to start flowing. Only long enough to put some plus charges here and some minus charges here. And what's going to happen is, like charges repel each other. Kind of remember that thing in high school physics with the little pith balls? You know, you charge them up, and if they're the same charge, they don't want to see each other. If you have two bar magnets and the north poles face each other, you can't get them together because they repel each other. If you put the north and south together, bang, they suck each other into their existence. Same thing here. Plus, plus, minus, minus. This thing gets more minus charges and more plus charges here, and every plus charge here repels every new charge that arrives. And what actually happens is, as soon as, and this is time, I use the Greek letter tau, and this is voltage across the capacitor. As the capacitor charges up, it flattens out. Basically, it actually stops before it gets there. Asymptotically, meaning forever it takes in theory, but eventually gets there. It charges up and then it stops conducting. When the charges here equal the potential difference here, it's all charged up. If this thing is 10 volts here, this thing is 10 volts here, and you're done. It took time to get there though. This thing has enough metal in it that it can actually absorb charges, and as it absorbs them, additional charges show up until you have enough charges here that got the same potential here as you have here. They're equal, they're opposite, they kind of repel each other, and they say you can't put any more in here because the voltage here is the same here. Or describe it differently. If I had a 10 volt voltage source here, 10 volts, this and and this are equal and opposite, and no current's going to flow. This guy here, the current is going to be 0, because the potential difference is 0. This potential and this potential are the same. There's no difference of potential. When you don't have a difference of potential, you don't have a voltage. When you don't have a voltage, you don't have a current flow. So this guy's going to charge up until that condition exists. Potential here equals the electromotive force here. Bang, you're done, you're stopped. You're at this point in the time evolution. At that point, you're fully charged. Okay, so what good is that? Well, obviously one thing to do is you can store charges in it. You charge it up, now it's like a little battery, put it on a load, the charges bleed off, now it's a dead battery, now you go charge it up again, discharge it, charge it up again, discharge it. There are some circuits in the world that do that. They charge a capacitor as like a small battery. And it does work very effectively for that purpose, as long as you don't try to draw too much current out of it. Let's do something that's more to the purpose for which the capacitor really was invented. After we charge this thing up, let's reverse the voltage source. And let's put a minus charge here and a plus charge here. Well, what do you think is going to happen? This minus will attract these positive charges, and now you're going to have the current flow in the opposite direction. And all these plus charges are going to show up here, and all these minus charges are going to show up here. And their potential is going to drop to 0. But it's not going to stop. It's going to keep going until you have pluses here and minuses here. First you're going to charge it up, then you flip this thing around, then you're going to discharge it, and you're going to charge it again, but in the opposite direction. Now the opposite plate is charged negative, which was once charged positive. Think about that for just a moment. I just made current flow through the capacitor because it flowed this way until it couldn't flow anymore, and then it discharged and charged this way to a negative potential, a minus V. If I keep doing that, if I keep flipping this thing back and forth, the current will flow until it charges, the current will flow the other way until it charges up. What if I flip it back and forth faster than this time period that it takes to fully charge it? Like, what if I feed it an alternating current? You'll charge it up this way, then you'll discharge it and charge it that way, then do it again, do it again, do it again, do it again. And that's exactly what happens. When you put an alternating current through a capacitor, the current flows through the capacitor. But it doesn't, because you got this dielectric here. That's a non-conducting path. This thing's an open circuit. This guy and this guy are not connected. But effectively they do conduct, because you've got enough surface area. The plates are here with enough metal to absorb enough charge that you can actually charge it one way, charge it the other way. And you got this electric field here, and of course it reverses itself. The electric field goes here. You not only have the metal here, you got the attraction of the opposite charges on each set of plates. Even though there's a space between them, there's a field between them that kind of makes the charges want to flow into that. Until there's so many of them here, they repel further charges from the place that the charges came from. Therefore, as I said, a resistor is time invariant. It doesn't matter if it's AC or DC. Current flowing through it is, if this is 0 and the current looks like that, no problem. If the current is like this, no problem. Well, the capacitor is a little different. If it's DC, it's going to charge up and stop. If it's AC, it'll charge up, discharge, charge the opposite way, discharge, charge the first way, back, forth, back, forth, back, forth. And current really will effectively go through the capacitor. Pretty clever, huh? What about that other guy, the inductor? Does he do anything like that? Sort of. A little differently, but the results are kind of the same. Let me show you what happens with an inductor. It's a guy named Michael Faraday, who's supposed to be the inventor of the electric motor. And he built out a principle that came from a fellow named Ampere, a Frenchman. Came up with a very interesting discovery. Ampere, of course, is where we get the ampere. Ampere is where we get the short form amp, I, that we use, that we measure in amps, or abbreviate the amps with an A. So the I is measured in terms that are abbreviated with A. I is current flow, amperes is the, or amps for short, is the measure of the current flow, and A is the abbreviation for the ampere. Just like a guy named Alessandro Volta invented the electrovoltaic cell. He did that with typically two pieces of dissimilar metal. You can do this yourself at home. Take a nickel and a penny, or a dime and a penny, just two dissimilar metals. Take a piece of cardboard, put it in between, dip it in salt water, do a stack of them, and you'll feel a little tingle in your fingers. It will be a battery, and it will really produce a voltage. So Volta came up with that electrovoltaic cell, and after him we named the volt, which we use either this symbol or this symbol. You can use either one. This I use typically when I mean electromotive force. This one I tend to use when I mean voltage drop. Same thing. One's the source of the potential difference. One is the resulting potential difference when you force current through a load. And volts is the term, and abbreviation is V. It's not E. Volts is V. All right, let's talk about that inductor.